Parallel killers and inhibitors. Let's do this one real quick, and then we will take a break after it. We are going to mostly do demo with our parallelism killers and inhibitors, because sometimes we could be over our cost threshold we could qualify to go parallel, but something about our query just keeps us from going parallel. Let's open up parallel killers and inhibitors, and we are going to roll at maxed out 4 and cost threshold 50. Some examples of parallel inhibitors. So right now I've lowered my bar for parallelism down to 50, which is way low for these queries. These queries all estimate out at above 50. There is some parallelism, some inhibitors only impact part of the plan. One parallelism inhibitor, it's not a parallelism killer, it is top. The top property only impacts part of the plan. This first query here does not use top. The second query does use top. We're doing top 100. We are going to do Control L to compare these plans. And these plans are going to be different because one query uses top. This query uses top and the other query doesn't. Top is a parallelism inhibitor, but it only, notice that I do have parallelism over here. This only impacts a zone of the plan. Top is only going to impact the operators around it. And notice that for this query, SQL Server actually didn't want parallelism for a lot of this. It didn't want to do the sort in parallel. Well, that's fine over here. You know, so this, yes, top is a parallelism inhibitor. Is it making this query much worse? No. I mean, there is extra work in here because we have a top operator and we didn't have one before, but right, it's so not every parallelism inhibitor is the worst thing in the world, is what I'm trying to say here. Some things that you'll see on the list of parallelism inhibitors, it's fine, it's for a zone of the plan, and oftentimes for something like top, I mean, hey, if it's going to limit the amount of results I get back dramatically, that may be a net win for performance instead of returning a ton of rows. Now, this doesn't return a ton of rows because it's doing an aggregate. Backward scans are parallelism inhibitors. Let's look at this. This is a different query, by the way. So we are not doing a group by in here. In this case, we're doing a top 100, yes, parallelism inhibitor for part of the plan. And we're querying from the first name by birth date table, ordering by fake birth date stamp descending. So I'm going to go ahead and create this index. It takes a couple minutes to create. What this query is doing is saying, I want to return 100 rows based on, this column is actually a fake birth date stamp. I have faked out 1 row per baby and they each have a made up birth date stamp because I only actually know what year they were born in. But if I'm ordering by fake birth date stamp descending, how are we going to use a non-clustered index that's keyed on fake birth date stamp ascending? In the definition of this index that is created, I have low fit, you know, whatever, however low my table goes. So let's say it starts at 2000. My birth date stamps are 2000, 2001, 2002, 2003, ascending. I do have the option when I create an index to create it descending, but I didn't. But my query is doing descending. So the sort order in my query doesn't match the sort order in my index. SQL Server can do a backward scan of that index. It can say, oh, you want the most recent ones. Now you're ascending in the index. I can go to this other end of the index and scan backwards. But that portion of the plan that does the backward scan, it can only be single threaded. That means that my query has 2 and my index did create after a minute there. I have 2 parallelism inhibitors in here. I have a top, and then I have a parallel scan. So I'm going to do an estimated plan on this guy. And note that SQL Server, for this, creating the index for this has made this query pretty darn cheap. My estimated subtree cost is 0.3. I am below 1 for my subtree cost. If I am letting SQL Server decide, it's going to do this single threaded and it can do it real fast. But what if I tell it to use this undocumented hint, enable parallel plan preference? I say, ignore the cost threshold. What does the plan look like here? I'm going to go ahead and execute this with actual plans on, and it is still fast, but look at this, what it's doing here. It has decided to, if I look at the properties of this index scan, it is using my index I created. It is saying, I am going to do a backward scan on this. It decided I'm going to do a backward scan. And yes, you told me you wanted to go parallel, but I can't do this part parallel. So I'm going to do this single threaded, and then I'm going to distribute streams and do these things in parallel, and then gather the streams together and go back. Because it cannot do this backward scan in parallel. If I create my index with the other direction, and this will take a minute as well, I'm running this as well. Now we are in our index changing the sort direction so that most recent ones are to the on one side, on the opposite side of the index. I am now making my query sort order match my index sort order. Otherwise, the definition of the index is the same. The index before was keyed on fake birth date stamp, include first name ID. I'm creating it. I can specify max stop on index create. How many cores do I want you to use? Data compression is row. This might actually do better, by the way, at a higher DOP. I simply don't want to overwhelm the server while I'm presenting is the main reason I have that at DOP 6. Drop existing, can reuse the existing index structure. But yeah, everything's the same except for the descending here. Once I do that, even if I force it to have a plan, it is going to match up. It doesn't have to do a backward scan anymore, so it will have the option to do that the other way. Our index is almost created. We're at 1 minute and 4 seconds. And let's paste this into a new window. It hasn't created yet, so when I do estimated plan there, oh, that's interesting. Oh, it just finished. I was like, I got the new plan, but it had just finished. Now that I have the index order matching the scan direction in the query, I do get a parallel plan. My scan direction, oh, that's interesting. It doesn't always show you scan direction forward. Sometimes you just, if it's not a backward scan, you usually see just the absence of that. So that is interesting that I did get scan direction forward. I wonder if that's just new based on a request, or maybe I just haven't noticed that. But even if I do the same thing in this window, now I can, because it is a forward scan, I can use parallelism there. So this is going to be a little bit faster than the other way. The other query was very fast. This, it can use multiple cores. The truth is that this query now doesn't need parallelism though, but that might be useful for tuning sometimes. It might be useful for tuning sometimes. The true evil though, I cannot drop the index because I'm using the wrong name. Let us drop the index with the right name. We will paste in the right name there, and now we can drop the index. The index that can't be dropped because it has a different name. The true evil when it comes to parallelism, for now, this may change in the near future because SQL Server team's working on functions, is user-defined scalar functions in SQL Server. I am going to create a terrible function. This is terrible in multiple ways. This is a pointless scalar function. It is named return that thing. It takes an int in, and it returns a tiny int. So it could take in a value that it then can't return and could break. Right? It's terrible. But also, it's not even operating on the value. The only operation it's doing is changing the data type. And honestly, it's only doing that because I am sort of a terrible person. So we have a function that is just taking in an integer and then it's returning a tiny int. If I compare execution plans for this query, and the only difference, this is our normal query at the top who's doing the aggregation, and the second one is saying return that thing around the count. So it's performing the aggregation and then moving it into the function. If we compare the plans for these queries, the one who doesn't using the function, now that I've dropped that index, it's like, oh, I need to go parallel because my estimated cost to run single threaded is higher than cost threshold. But because I added a reference to a user-defined function, my second query here, it can't go parallel. It's the one with the UDF, no parallelism. It just kills it. And this is one of the reasons that user-defined functions are kind of hated by a lot of people. If I run, I will make it return an int. So let's make it not throw an error. So I'm going to alter my function so it returns an int so it doesn't fail. It is kind of fun because when you run this and it fails at the very end. It executes the entire query and then fails. My first query, who can go parallel, it comes back right away. My second query, who's going single threaded, it's going to take it 47 seconds to finish because I added in a user-defined function that means that it can't go parallel. It's a scalar user-defined function specifically. This is not there are other types of functions that may not kill parallelism, but scalar UDFs, so sad, so sad. T-SQL scalar UDFs, I should say. All right, so let's go ahead and look at another thing. I have found this one before. It's more rare. User UDFs are the most common thing. We're going to add a computed column to our table ref.firstname. Ref.firstname is a tiny column. So I am adding a computed column. The computed column uses my user-defined function. I added a new column that is named that thing. That thing is the total name count column on the table, which is now been wrapped into the return that thing function. Notice that our query does not use either column. Our query does not care about total name count. Total name count is not in here. Our query does not care about that thing. Our query is only using, on ref.firstname, it only is using it to actually get the first name that we use in the predicate here. Well, it doesn't matter that we aren't referencing this because there is a computed column on the table that references a user-defined scalar function. Parallelism for anyone who references that table is now disabled. I had one customer system once with a really smart group of people who were, they were really good developers. If I run this, it'll take 47 seconds. But they were confused why their app wasn't scaling. And I started looking around at the query plans and I just noticed like, hey, we've got a lot of, everybody's going single threaded. Like all our biggest queries are not going parallel. And I started looking at their cost and I looked at their cost at DOP1 and I was like, well, cost threshold isn't preventing it. They should be qualifying for parallelism. And it turns out they had user-defined functions in computed columns on some of their core tables that they just joined to all the time. And it meant that none of their queries could go parallel. So they had very large enough queries that being single, it was like everything was at max DOP1. And so that had to be removed from the system. So scalar user-defined functions are trouble. Scalar user-defined functions in computed columns are extreme trouble. Now that I have dropped my computed column, I can once again do, I automatically get a parallel query. Also, system table access or system function use will kill parallelism. I have now added in a query for sys.objects in my query. Everybody's going to go parallel. Whole plan will go parallel. Same thing if I use object ID in my query, it's single threaded. So we don't, the only time in user queries that I've been tempted to mix those in application queries have been in systems with table partitioning where I wanted to do a workaround that used some system calls to figure out how many partitions we had. You want to segment those into their own queries because they kill parallelism. There is a greater list of this at Paul White's blog. The blog is called Forcing a Parallel Execution Plan, and it lists the inhibitors. Very, very helpful blog. And this blog post was what helped me figure out to look for the scalar T-SQL UDFs in computed columns. So it saved the day there. Very, very good stuff. The most common causes of parallelism inhibitors that I see, the things that kill parallel things are, in fact, the winner here. The most common cause is user-defined functions. Scalar UDFs are the biggest parallelism killer that I have encountered. Don't. So if we are seeing important single-threaded queries, the steps that I would take is I would try to figure out, okay, why aren't you parallel? What is your estimated cost at DOP1? Are you simply under the cost threshold? Do you have a scalar function in there? And usually it's going to be one of those two. Or is there something else happening that is one of the parallelism inhibitors? And that blog post can be incredibly useful.